Oi, pessoal, vamos começar o seminário dessa semana. O seminário, the seminar will be given by Marilia Carlos, who has a bachelor degree with a specialization in astronomy from USP, and she did a master's at INPI and a PhD also at USP. And she completed a doctoral sandwich program at Monash University in Australia. And in 2018, she was a postdoc in Padova in Italy and Uppsala in Sweden. She's currently a researcher at the National Observatory here in Brazil, working with stellar chemical analysis using high-resolution spectroscopy. Thank you very much, Marilia, for accepting our invitation. You may start when you're ready.
Okay, thank you. So, good afternoon, everyone. First of all, I would like to thank you, the organizers, for the invitation. It's a pleasure for me to present my work for you guys. So today I'll talk about my recent research, which is based on high-resolution spectroscopy, and the title of my talk today is Detailed Chemical Composition of Solar-type Stars with and without planets. For some context, we know that the first exoplanet around the solar-type stars were observed in 1995. Here we have, for comparison, the Sun and the star, which is a solar twin, 51 Pegasi. And we have also the distance, the Sun and the distance of the planets, Mercury, Venus, Earth, and Mars. And also for 51 Pegasi, the distance between 51 Pegasi and 51 Pegasi b, the planet discovered. Because of the limitations in instrumentation, we have this bias in observation, so it's more easy to observe massive planets that are near the stars and the host star. And because of that, we, in the beginning at least, we observed a lot of what we call hot Jupiters, right? Those planets that are massive as our Jupiter, but are very close to the host star. And of course, the instrumentation evolved with time, but we still have a limitation. So today we can at least talking about solar type stars, right? We can observe for Earth, but we try to push this. The dream was to push this to Earth-sized planets, right? So since the discovery of these first exoplanets around the solar type star, we have more than 5,000 exoplanets observed by now. And the idea here is why to study the star is to study the composition of the star, because we know that the star and their planets were formed from the same cloud. So the limited abundance of the host star can put first further concern on the chemical composition of their planet. And when we do that, the stellar composition can offer a promising way to investigate and understand how those systems are formed. So this is the idea. So to illustrate that idea, we have this work from Juan Beach from 2023. So we have the star, and we have this protoplanetary disk. So the star is still information, and along with the protoplanetary disk that may present planets in the future. So what we have here presented is that this protoplanetary disk or stellar disk have a lot of species, and we can separate the species by condensation temperature. So near the star, we have what we call the highly refractory elements, followed by the moderately refractory elements, and then the volatile elements. So the volatile elements are found only further away from the star because they have lower condensation temperatures. So near the star, these volatile elements were evaporated, right? So if we put a planet at some distance from the star, and this distance will depend, will differ the composition of star in the end according to this model. So if we put a planet here, this planet will prevent all this material further away from the planet to fall into the star atmosphere. So the idea here is that the planet will stop some material to follow into the stellar atmosphere. So this would cause a difference. So if the star doesn't have a planet, as in the first, in the top panel here, all these species will fall into the atmosphere, but if you have a planet, some of them wouldn't fall into the stellar atmosphere. So the idea here is that because of that, maybe then there is a difference in the chemical composition of similar stars. But when you consider that one star has a planet and another doesn't host any planets, that's the idea here. So if you go back to 2005, so since the discovery of the first planet around a solar type star, people started to study those stars, those host stars, to see if they are special in any way. And there is this paper from Fisher Valente in 2005 that showed that for stars that are more metal rich, the probability of those stars host a planet is higher, it's greater. So the idea here is that because we have more iron content, this would facilitate a formation of a planet around that star. So that was found. Later in 2009, Melendez and collaborators, they studied the sun in comparison with other solar twins. And solar twins are stars that are very similar to the sun when we talk about stellar parameters. So those stars have effective temperature, surface gravity, and metallicity very similar to the sun. And here in this study, what was interesting is that we know that the sun hosts planets, right? But those solar twins, they didn't have planets detected at that moment. Actually, until today, I checked very recently, and those solar twins studied here in 2009 doesn't have planets detected. So what they did was perform a high-resolution spectroscope analysis, and for the sun and these 12 solar twins, and they compared then the chemical composition of the sun with what we can call an average solar twin, which was an average of all these 12 solar twins that they studied. And what they found then is that the sun is missing refractories in comparison to volatiles when compared to those solar twins that it doesn't have planet detected. So the idea here then is that these missing refractory were used to form our terrestrial planets. This is why in the Melendez view, this is why the sun is refractory poor. Later, Bedell and collaborators in 2018 performed a similar analysis, but now with a greater sample of solar twins. In this case, I think they analyzed around 75 solar twins, if I'm not mistaken. And in this sample, I think 3 of the 75 stars are hosting planets. And what they did this time was then compare the sun with the twin. And then we have here in the y-axis the abundance, and in the x-axis the condensation temperature of the elements, and we have each element carbon to SNR process elements, I guess. And what they did then was to make a linear fit using only the refractory elements. So from zinc to, I don't know, maybe samarium, I don't know what is the last one here. And they then made these linear sheets, and they compared the slope of those linear sheets. So by definition, the slope of the sun is zero because we are comparing the sun with the sun, the way they construct this analysis. And then we have the slopes for all the other stars compared to the sun. And what they found can be summarized by this histogram here on the right. And what they show here, it's first of all, they did the correction due to the galactic chemical evolution. So we know that stars born in different places and times can have different chemical composition itself. And because we are trying to compare the sun with those stars, they try to correct by the chemical evolution of our galaxy. And what they found then is that the sun is refractory poor in comparison with, I think, 85 or 90% of the sample. And this is in agreement with what Melendez found in 2009. Another work in 2021 by Nibauer and collaborators did the same analysis, but now not with a high resolution spectra, because they use apogee. The work of Bedell and Melendez, they were using HARPS spectra. Now Nibauer made this analysis with somewhat lower resolution using apogee spectra. And what they found can be summarized in this histogram also. So they found two, let's say, subsamples. One is the depleted stars here on the left. So the majority of stars they consider as depleted stars, and some stars they consider not depleted stars, and depleted in refractory elements here. So the average of not depleted stars, so the slope rate, it's here presented by this blue dashed line, while the average of the distribution of depleted stars is represented by the red dashed line. And the sun here is the black dashed line, zero by definition, right? So they found that, okay, the sun is more similar to the depleted stars in refractory content, but still a little refractory poor. Another way to compare or try to assess the importance or the fact that the one star hosts a planet and in comparison to other stars that it doesn't host planets is look at binary systems. Now, because we do not have to care about the chemical evolution of our galaxy, and because we know that in binary systems they were born from the same cloud, so if you see some difference, might be due to the presence of planets or not. So this work from Spina 2018, they studied 100 solar analogues in binary systems, and they focused on iron content and lithium content. I will explain later why lithium is important in this context. But what they found is that based on the content of lithium, or the excess in this case, of lithium in some stars, because they compared pair by pair, right? So based on the excess of some pairs, of some stars in the pairs, they claim that 25% of stars might have engulfed planets. Later in 2024, the work of Liu and collaborators did some analysis on 250 solar analogues, again in binary systems. But now they look at several elements, not only lithium. And what they did was comparing pair by pair the chemical composition or the difference in chemical composition of those stars, to try to see if they find any pattern in these stars, because they host planets or maybe engulf the planets, etc. So they found that for some stars, they have a pattern that is compatible with a planet engulfment. So here we have in dashed blue line a model for ingestion of planets. And we see that this pattern is compatible with the ingestion of planets. So what they found here is that in this sample, at least 8% of the stars might have ingested planets. Now talking a little bit about lithium, as I mentioned some slides earlier. Lithium is very interesting because it's a light element that it's burned easily, so it ignites at 2.5 million kelvins. And when we are talking about solar type stars, we know that we have a convection zone, right? And at the base of this convection zone, the temperature is around 2.2 million kelvins, which is not enough to burn lithium. So the idea here is that the lithium in the surface of the star is dragged down to the base of this convection zone, and then some extra mixing process are sending the lithium even more inside the star when it can be burned. So lithium is interesting in the context of planet engulfment or presence of planets, but also because of to understand the stellar structure. So many years ago, the discussion was whether which were the main factor of lithium depletion. So some groups discussed the presence of planets would be the main reason of lithium depletion, but other groups said that it were due to age. So why do you think the planets would be a reason of lithium depletion? The idea is that the presence of planet would change the angular momentum of a star. This change of in angular momentum would change the depth of the convection zone, and then this the lithium would be more easily burnt inside the star. So what they showed here, this plot on the left, is that the work from Delgado Mena and collaborators in 2014 is that stars with planets here presented by the green and red dots have less lithium in comparison with stars without planets presented by these blue open circles here because of the presence of planets. But of course, here is just a tentative, I would say a tentative way to find something. It's very weak correlation. Then with age, we have a more clear tendency here. So what we have here is in this plot on the right is the content of lithium on the y-axis plotted against age. So what we have here is the sun here, and we have some line and dashed lines. We have some solar models, and represented by triangles, squares, and this star we have some solar twins. These solar twins are very similar to the sun. The only difference is the age, and we can clearly see here that younger stars have higher content of lithium in comparison to older stars. This is what I said before. So maybe the lithium is gradually burnt as the star ages, so older stars have less lithium in comparison to younger stars. And this here we can only see that when we are talking about solar twins, right? Because they are very similar in the other stellar parameters. The only difference here is the age. So what we see here is just the effect of time. So if we go to 2019, I published a paper, and what I did was analysis in a broader sample of stars, because if you go back here, we have only 1, 2, 3, 4 solar twins in comparison to the sun. So we increased the sample to around 75 solar twins. And what we found is, of course, the age is the main factor to lithium depletion. We can see here in this plot on the left. But if we see in the region of the sun and the where we have stars with similar age to the sun, we can see that the sun is lithium poor when compared to the stars with similar age. And so what we did, what we tried to do at least, was to take a subsample of this bigger sample. In this subsample, we selected stars very, very similar. I mean, we are talking about solar twins. They are very similar to the sun already, but we tried to cut even more in a smaller range of stellar parameters. And we then did this linear fit here to represent how the lithium correlates with age. And what we found here is, of course, just let me say that these gray, purple, and blue shaded areas are the 1 sigma, 2 sigma, and 3 sigma interval. So what we can see here is that, okay, we have a strong correlation with lithium and age, lithium depletion and age, but also that the sun is at least 2 or 2.5 sigma lithium poor in comparison to the average of the, or to the expected lithium for its age. So what we did then was to make a difference between the expected lithium given by this dashed line, these linear fits, minus the observed lithium for each star, and we call this delta lithium. And we plot against the condensation temperature slope that I showed earlier. So this data of this condensation temperature slope was taken from the work from Bedell because we work with the same sample of stars. And what we found here then is that the sun is the most refractory poor star in the sample, also the most lithium poor star in the sample. So here we have somewhat tentative correlation. The experiment that I think gave 0.5 index of correlation, so it's not a strong correlation, but we can see more or less that stars with lower lithium content have lower condensation temperature slopes. So maybe the fact that the sun is very lithium poor is related then to the presence of planets. So maybe the sun is the way that we observe because of the unique, our unique solar system structure. Of course, there are other abundance ratios that we can see. We can investigate to try to infer if there are any difference between stellar chemical composition for stars with or without planets. And some of the most famous abundance ratios are the CO, the carbon over oxygen, and the magnesium over silicon ratios. So here we have this work from Delgado Mena from 2010, and we can clearly see a difference between the content of carbon on the top and oxygen on the bottom when we compare stars with planets in red with stars without planets detected in blue. In 2019, Pavlenko also analyzed a sample of stars with and without planets. And what they found here is we have stars without planets in blue and stars with planets in red. And what they claim is that the ratio of carbon over oxygen it's greater for stars with planets in comparison with stars without planets. Of course, what we can see here is a tentative, let's say, a difference. It's not a strong conclusion here, but then the work from Amarsi 2019, they tried to reply this, but now with more precise and more accurate results. And what they did here, first they selected more clean line list, let's say, and also they perform a 3D NLTE analysis, so a more accurate analysis. So on the right here, we have the 1D LTE analysis. And we can see that for stars without planets that are represented by the black squares in comparison to the stars with planets, which are the blue circles here, much of a difference. But in 3D non-LTE, we can see clearly that there is a tendency for when we go for the metal-rich, metal-poor search, the most metal-rich stars, the stars with planets have more content of CO in comparison with stars without planets. And this is only possible to see because they did analyzing 3D non-LTE, so the most accurate possible way to infer those abundance, chemical abundance. So to talk about my current work, then it's a follow-up of this 2019 analysis. So what we did was study the same sample, but now extend the analysis for other elements, and we published the paper last year with those results. So the paper is called "The Peculiar Composition of Destinies Not Related to Giant Planets," and I will show you later what do we mean about this. And this paper was done by me and Anisha Amarsi, Poetic Nissen, and Gloria Canuck. So Anisha Amarsi and Gloria Canuck helped me a lot with the non-LTE determinations. And Poetic Nissen is a legend in high-resolution spectroscopy. And I did this when I was at Uppsala University doing my last postdoc. And I just want to say here, just a parenthesis, that Uppsala University is a very nice place to work. It's a great university. It's one of the oldest university in Europe. But the place is very cold, so it's very hard to live there. But it's interesting, actually. It's a life experience because I could experience the midnight sun, for instance, because there in the summer. We don't have nights, let's say. So it's very interesting, and I could see also the northern lights, so it's amazing. So it was a very good experience. So going back to the the work, to the analysis, so it was the sample consists of 50 solar type stars observed with a high resolution with the HARPS spectrograph. So we have really high resolution and a good signal to noise. I put here that the signal to noise was greater than 200, but in reality, most of the stars had a signal to noise around the 1000, so it's like a really good spectrum. In this sample, 21 stars didn't have planets detected yet, and 29 were hosting planet stars. And in these 29 stars with planets, I think most of them were giant planets, as I'll show you later. And I think 3 stars host planets with super Earths. So we perform a chemical abundance analysis from carbon to zinc, and we did the analysis in 1D LTE, and when possible, we did the 1D non-LTE, 3D LTE, and 3D non-LTE corrections. So the stellar parameters, effective temperature, we took it from Nissen 2014, and microturbulence velocity and iron metallicity we took from the work from Amarsi, and we updated the values of surface gravity using Yosemite isochrons and guide year 3 data, and we also calculated the ages. So the analysis, the summary of analysis was that we took the stellar parameters, built a stellar atmospheric model, and this was 1D Marx models. Then we took some line broadening information, a line list with atomic data, and put all together in this radiative transfer code called MUG. And MUG is a 1D LTE radiative transfer code. And then we get the 1D LTE elemental abundance. Then we corrected this 1D LTE abundance for 1D and 3D non-LTE departures when possible. There were some elements that we couldn't correct. So this is just to summarize the corrections. Here we have the example of sodium, magnesium, silicon, and sulfur. And here we can see that what I'm showing is the absolute corrections in comparison with the effective temperature of each star. And we can see that the corrections are non-negligible when we are talking about absolute corrections, but and for some elements they are negligible, actually, for sulfur here, for instance. But because we are doing a differential analysis, when we measure the differential non-LT corrections, they became more or less very small. So the results, of course, we did look at the lithium again, and this time 3D non-LTE lithium, abundance of lithium. And because we have these solar type stars, not only solar twins, we could not see any strong correlation with any parameter, because this abundance depends strongly on effective temperature, but also on age, so it was hard to disentangle both. But if we look at the box here near the solar twins realm, let's say, the range, we can still see that the sun is lithium poor, even when we go to the 3D non-LTE analysis. So this is in agreement with all the results. We also did then a similar analysis as presented in Bedell 2018. And here we have then the abundance in comparison with condensation temperature. And what I want to show here, first of all, these two plots are for two different stars, just to show two random examples. What we have here is in black is 1D LTE abundance, and in red is 1D and 3D non-LTE abundance. So we can see that for some elements there is no difference, like for sulfur and aluminum, and maybe sodium, it's a small difference. But for other elements like carbon, oxygen, and magnesium, the corrections are very important. And titanium was very important for some stars as well. So what I did is do a linear fit in this refractory range, right? And we did then two fits for each star. One only consider 1D LTE abundance, and the other consider the non-LTE abundance. And then we compare these slopes, right, in the same way as Bedell did with the stellar parameters, to see if we find any correlation. And for effective temperature and surface gravity, we didn't find any correlation. This is the same case for microturbulence velocity, but we did find a correlation, and a strong correlation, with these condensation temperature slopes with the iron content of each star. So what we are seeing here in this plot on the right is that more metal poor stars have more content of refractory elements in comparison with the more metal rich stars. Another thing that we can see here is that we also perform a linear fit for the stars with planets in blue and the stars without planets in black. And there is a difference, but I think they are 1.5 sigma compatible, if I'm not mistaken. I don't remember correctly now. And what we can see here is that from here, it seems that the sun is still refractory poor in comparison to the stars at similar metallicity. So this dependence with the condensation temperature slope with metallicity is just a signature of the chemical evolution of our galaxy. But when we look at stars with similar metallicity as the sun, we still see that the sun is refractory poor. So to try to understand how the impact of the chemical evolution of our galaxy in our sample, we try to do the same analysis, but now only consider alpha elements and then only consider non-alpha elements to see if there were any differences, because these different type of elements are producing different sites and have different time scales. So we try to make this different to try to infer more or less if there were any difference. And what we have here is the condensation temperature slope against the stellar metallicity, and in this case, we separated in beams of metallicities. And we have here in open symbols stars with or without planets, but only considering alpha elements. And then in the filled symbols, we have stars with or without planets, but considering the non-alpha elements. And in general, what we can see is that there is no difference. There are 1 sigma compatible with each other. But when we go to higher metallicities, we can start seeing a difference between the stars when you consider only alpha elements and non-alpha elements. But the main goal of this paper was to compare stars with and without planets. And if you consider the group with and without planets, only considering alpha, they are still comparable. And if you consider the non-alpha, they are still comparable. So the message here is that separating alpha in alpha and non-alpha elements doesn't make much of a difference. So we try to also compare these slopes with some planets parameters. So on the left, we have the condensation temperature slope compared with the planetary system mass. And here what we did was sum all the masses of all planets in one system together. And on the right, we have the condensation temperature slope compared to the planet distance. And in this case, we plotted each planet. So this is why we have more dots here. So what we can clearly see here is that the dependence with iron content, right? Because these circles are color-coded by metallicity. And you can clearly see, as we saw in the plots earlier, that we have stars that are more metal-rich have lower slopes, condensation temperature slopes, in comparison with stars that are more metal poor. So in order to try to erase this metallicity effect, we did we calculated a delta T as in a similar way as we did for the delta lithium that I showed before. So we subtract the expected value given by the linear fit with the actually observed value of this condensation temperature slope. And then we plot this, what we call delta T, against the planetary system mass and the planet distance. And here we can see that we then erase this metallicity effect. And what we can see here is the sun in comparison with the average distribution here is refractory poor when we consider the planetary system mass and when we consider the planet distance. So what we can conclude here is that the fact that the sun is refractory poor is not related to the presence of giant planets. Because even when we compare our sun with the stars that have giant planets, the sun is still refractory poor. So to conclude my seminar, the takeaway message for now, the one thing that we can say for now is that high precision abundance are important to shed light on planetary system formation, and I would say that accuracy is very important as well. So I know that non-LTE chemical abundance are very hard to obtain because they have a high cost computationally speaking, but please use when possible because it's important to make a difference for several elements. And also that the sun being refractory poor is not related to the presence of giant planets, as I showed in my final plots. But it is still on debate why the sun is refractory poor, and this is included why the sun is also lithium poor. So that's it for me. Thank you.
Thank you, Marilia. Do you have questions? Thaisa already. Just tell us if you hear from there.
Let's see. Yeah.
Hi, Marilia. Thanks for your nice presentation. It seems that the main parameter here is the gradient of the condensation temperature of the what refractory elements. So I would like to understand this parameter better. I saw your results, but would you explain a bit better?
Okay.
Parameter, the meaning.
Yeah. Okay, let's go back a few slides. Let's see. Can you see these slides from Bedell?
Yeah.
Okay. So here, or maybe this one from Melendez, what we are doing is comparing the sun with another star, right? A solar twin or a solar type star. And this gradient is given by this slope here, the inclination of this linear feet. So depending on how inclined this is, this will give us estimation of how refractory poor the star is, or refractory richer in comparison with the sun, because the sun is the more refractory poor.
Okay. So this is the this is the slope of the.
Yeah. So all the other results that I showed, it's I said it's the condensation temperature slope is the inclination of this part here. So what Jorge did here was considering all the elements, the volatiles and the refractory elements. But from the work of Bedell, they started to not ignoring, but let's say left aside the volatiles, because the temperature are not that precise and it's more complicated to take them into account. So we are only looking at the refractory elements, what we can consider from zinc or sodium, let's say. And then we look at we perform a linear fit here, and then look at the inclination of this linear fit, what we are calling slope.
Okay, thank you.
Thank you. We have one more question here. Oops.
Can you hear me, Marilia?
I think yes. Let's try.
Okay, I try to speak up very long. So thank you very much for the very nice talk. It's very interesting. I have a question. So you were proving that the chemical abundance of the sun has nothing to do with the presence or not of planets, right?
Giant planets, yes.
But okay, assuming that because of your Jorge, his argument is that the chemical abundance of the sun is because these elements are in planets and small bodies in the solar system, right? Does anyone did the exercise of computing if all the elements that are present in planets and the small bodies in the solar system could account for this lack of elements in the
yes, sorry. Yeah. I really don't remember the details, but yes, some people did that. And the thing is that I think some people did let's say, just throw Earth on the sun, and then diluted this. And we can see this for a while, this difference for a while. And it is, I think, compatible with this difference that Jorge has observed in his work. But the thing is, this will be diluted over time. Like 50 million years later, this signature is erased. So, yeah, there are some works on that.
Okay, so in summary, it would be compatible.
Yes.
Okay. Interesting. Okay. Thank you.
More questions from YouTube? Is there, so I have a question regarding the first point of your conclusion about the computational time. Can you speak a bit more about it, and whether
Talking about the non-LTE, you mean?
yes, the non-LTE, and
Yeah, I mean, it's more accurate.
And
Yeah, yeah, exactly.
the new generations of supercomputers might be able to help and so on.
Yeah. So I think I'm not the best person just to talk about that because it's not my expertise, but I work closely with people that do that. And it's more accurate because the way that you treat the physics inside the star, right? So let's summarize as that. But this can take months, like 3D NLTE. It can take in supercomputers. It takes like 1 month to produce, like because what they do, because it takes months to compute that. It's built grids, right? In the similar way as you built for the stellar atmosphere models. So they built these grids because, for instance, for sodium, I was working closely with Gloria Canocchi, and I think it's half of her PhD was to build this grid of one element, sodium. And when I asked specifically things for her, she was able just to answer me after like 3 months. So it takes months.
Okay. Do we have more questions? If not, let's thank Marilia again. And we were successful, no invasions today.
So thank you again for the invitation.
We're very thousands.
Tchau, obrigado.
Tchau.